promised you some time ago that there was really one major question we were going to be asking in organic chemistry. And remember what that question was? What are the blank going to do? What are the electrons going to do is our question, right? So if we can predict what the electrons are going to do, then we we know everything. So we spend a lot of time thinking about two factors that help us predict that. Number one, structure, right? Where are the electrons, right? What's the geometry of a particular system? Is it flat? Is it tetrahedral? Is it linear? Is it crowded? Is it crowded by solvent? Is it crowded by whatever, right? What's the structure? That tells us where the electrons are. And then we learn how strong the electrons are or how polar the electrons are, right? So if you have a polar bond, you know that the electrons are really more down toward the one atom than the other, right? If you have a polar molecule, you know the electrons are really over on this side of the molecule and rather than that side. Or if you have an ion, like a carbocation, you know that there's a nucleus that's available for attack. So we're really getting into this very much. This is a huge chapter. And if I can encourage you to really give this your heart, then much of what remains in organic chemistry, both organic chemistry 1 and organic chemistry 2, will seem like natural extensions of what we're going to learn in this chapter and the next. But I would say especially this one. All right, so let's start out with the concept of enthalpy. So enthalpy is a definition of it's the heat exchange between the reaction and its surroundings. So there's two factors that go into whether reactions are going to happen or not. And one big one, maybe the big one, is enthalpy, right? So breaking a bond requires the system to absorb energy. So we learned before, we learned in Chem 2 probably, Principles 2 or Gen Chem 2 about molecular orbital theory. We learned that if you have an atom and it's got an electron and another atom, it's got an electron, if they can, they'll make a molecular orbital or a bond, right? And so these electrons will go away from here and they'll go into the molecular orbital or into the bond. Well, they're lower in energy, right? So the amount of energy that it is saved, right? That's what this is lower energy. Pardon the phone here. I'm going to silence that. I figured out how to do that. So the amount of energy that's in that bond is indicated here, right? So the energy of the one atom, the energy of the other atom, their total energy, but they fall in energy in order to get down here, right? Well, that bonding energy is what is the amount of energy that it requires to break the bond, right? And that's the energy that's absorbed, okay? So let's talk about bond breaking. Well, bonds can either break homolytically or heterolytically, and we're going to see both of these. Homolytic is when they go back to where they were, right? Remember the picture on the previous screen, right? You've got these two atoms, and then they go, you know what? Hey, if we make a bond, let's leave here and go here, then we can save energy, right? Well, if we give the energy back to the system, the electrons go back up into it, and they got their electrons back, right? So X has his electron, Y has his electron, and that's called homolytic cleavage. It's sort of split in half, okay? Now, heterolytic cleavage is when both of the electrons go with one of the atoms. So when we're talking about bond dissociation energies, we're talking about homolytic cleavage. We're essentially going sort of backwards from here. Let's go back into our atomic orbitals. And that's what homolytic cleavage is, and we would draw it like that. Can you see a little single barbed arrow here? Little single barbed arrow. A single barbed arrow. A single barbed arrow is the action of one electron. A double barbed arrow is the action of two electrons. Okay, so some bond dissociation energies. We've got a table here. If you're going to do heterolytic cleavage of a hydrogen molecule, then the energy that's going to cost us is 435. Okay, 435 kilojoules per mole, right? We could calculate that out into any kind of units we wanted. A common one is kilojoules per mole of these bonds, right? If I have a mole of those bonds, it's going to take me 435 kilojoules to break those. Now, if I've got a hydrogen, I want to break that homolytically, that's going to cost me 410. If I want to break this one homolytically, it's going to cost me 569. right? That's what this is about. And more bond dissociation energies can be found in table 6.1. All right, so that's the enthalpy that's required to break a bond, and that's what these tables indicate. Now, most reactions involve breaking and forming multiple bonds. Okay, so an exothermic reaction is going to be when the energy gained by the bonds formed it's greater than the energy needed for the bonds broken, right? So in other words, it's going to be, exothermic is going to be lower in energy, and so we're going to get heat out of it, and that's what exothermic means, heat out of it, right? So the energy gained by the bonds formed exceeds the energy needed by for the bonds to be broken, and endothermic is just the opposite. Let's look at the energy diagrams for these. So an energy diagram for exothermic means that the enthalpy of the products is lower than the enthalpy of the reactants. I know you did this in Chem 2 probably, maybe Chem 1, Gen Chem 1 or Gen Chem 2. So if the energy goes down, then we get energy out of it and out of heat. That's what exo means. Exothermic is out of heat, right? So that if the products, however, have more bond energies, right, then it requires energy to be put into it. This is endothermic. Okay, I'm not sure. I think I may have said that wrong. If I may have said that if the products have more bond energies, what I mean is if the overall potential energy in the end is higher, then that actually means the bond energy is less. But this is how we're going to be drawing it with energy diagrams like this, right? So if the enthalpy goes up, then it's endothermic. If it goes down, it's exothermic. So we're gonna know then. We're simply going to rely very heavily on the sign of the delta H. If it's negative, it's exothermic. If it's positive, it's endothermic. I don't think I want to say anything else about that. All right, so enthalpy is our first big entrance into energies, and the energies are going to tell us what the electrons are going to do. They're going to give us a good indication of what things are stable, and we're going to gain tremendous predictive power by appreciating enthalpy.